When it comes to Saturn, it's hard to summarize just how lucky we were to have the Cassini-Huygens mission. 4 robotic probes have visited Saturn, but of those, Cassini-Huygens has hands down been the most impactful. And I mean that both literally and scientifically. Its data has provided the bedrock for over 4,000 research papers. It discovered 6 new moons and helped us better understand their composition. It survived 20 years, traveling 7 billion kilometers, and spent 13 of those years around Saturn itself, gathering data on Saturn's gravity, magnetosphere, its rings, and its structure. And Cassini kept gathering data right up until the last moments of its life, as it plunged into the mustard clouds of Saturn's atmosphere and ultimately broke into thousands of pieces. Couple that with the fact that it provided some of the most jaw-dropping, awe-inspiring images of Saturn and the solar system to date, and you have one hell of a mission. I'm Alex McColgan and you're watching Astrum. Join with me today for this Cassini supercut as we explore its grand finale, the period of time before the dive, what it discovered before and during its plunge, and the incredible discoveries continuing to be made to this day from the clues that Cassini-Huygens provided us. If you want to see Saturn's beauty, there is no better way to do it than through the eyes of Cassini in its grand finale. The first probe to reach Saturn was the Pioneer 11 probe in 1979. It was at this time that scientists confirmed that Saturn's largest moon, Titan, had an atmosphere. They knew they had to go back and visit the moon, but this time with a lander. Now, Voyager 1 and 2 were already en route to Saturn at that point, so naturally it was too late to include a lander with those missions. Thus, Cassini-Huygens was born, and in October 1997 it was launched into space. Getting a spacecraft to Saturn is no mean feat, as the whole trip was combating the gravity of the Sun trying to pull Cassini back to the inner solar system. So, to help achieve the speed needed to reach Saturn, Cassini used planets as gravitational assists. It flew by Venus twice, before returning back to Earth. Earth's gravity then slingshotted it towards Jupiter, which gave it the final push needed to reach Saturn. This alignment of planets, which allowed these gravity assists, only occurs once every 600 years, so timing in this case was crucial. And Cassini really scraped past Earth on the second time around too. It was only 1,100 kilometers above Earth's surface at its closest approach. This is made even more interesting when you realize what actually powered Cassini. It was by 3 RTGs, or radioisotope thermoelectric generators. Basically, the power source came from about 33 kilograms of radioactive plutonium. It's this radioactive decay which gave Cassini power, and even until the end of its life, it still produced about 700 watts. The issue with the spacecraft carrying this radioactive substance was that if scientists had gotten their calculations wrong and a crash landed on Earth, everybody on the planet would have been exposed to the radiation. Now, 33 kilograms spread out over the whole Earth is a very small amount, but in the worst case scenario, NASA estimated it would have caused about 5,000 deaths from cancer. They put this down as an acceptable risk though, as the chances of this happening were only 1 in a million. Cassini used RTGs because solar panel technology wasn't good enough at the time for the Sun to power something so distant. With RTGs, Cassini would have a very long operational life, and it might still be able to carry on even now if it wasn't for the fact it eventually ran out of propellant fuel. Cassini had numerous objectives: to understand the structure and dynamic behavior of Saturn's rings, explore Saturn's moons more fully, measure the magnetosphere of Saturn, study Saturn's atmosphere, and study Titan more extensively. This last part is where the Huygens part of Cassini-Huygens comes into play. You see, Huygens was a lander attached to the Cassini spacecraft, designed to see what was going on under the hazy clouds of Titan. Huygens is the part of the mission built and operated by ESA, the European Space Agency. The probe was only about 1.3 meters wide and weighed 300 kilograms. When it detached from the orbiter, it spent 22 days in space before entering Titan's atmosphere. The only system aboard that was active at this point was a wake-up timer, due to wake up the probe only 15 minutes before it entered the atmosphere. And when it woke up, what it saw was amazing. This video is an actual sped-up version of the 2.5-hour descent. The main mission of Huygens was actually about this descent, taking readings from the atmospheric pressure, its composition, wind speed, and so on. And because the mission was only to measure atmospheric readings, the battery life wasn't expected to last long beyond the landing. The scientists thought they could be landing on an ocean or lake, and so had designed Huygens accordingly. From what you see though, it actually landed on what could be the bed of a dried up lake. The mission for Cassini itself has been remarkably successful. As well as scientific data it has picked up over the course of those last 13 years, it has been able to provide some of the most stunning pictures found of space. I just want to showcase some of my favorites of Saturn. And of course, Saturn's moons are beautiful in their own right too, and some very dedicated souls have even taken 1 million photos Cassini has taken to show us what it would be like to be sitting on the Cassini spacecraft. These are real images. They've only been color corrected and enhanced and put in order to show movement. There's no CGI. It's simply amazing. As Cassini's fuel began to run low, scientists began to consider how best to get the most data they could out of the time they had left. To achieve this, they sent commands to Cassini, telling it to perform some very close flybys of the planet and some of its moons, getting closer to Saturn and its rings than it ever had before. Beginning on November 30th, 2016, Cassini repeatedly climbed high above Saturn's North Pole, then plunged to a point just outside the narrow F-ring, which is the edge of the main rings, completing 20 orbits in total. Then, on the 22nd of April 2017, Cassini would leap over the rings to begin its final series of daring dives between the planet and the inner edge of the rings. This was the Cassini Grand Finale, a series of loops and dives that brought the probe closer and closer to its object of study, facing greater and greater danger as it flew, until finally, as its data became purest, as Cassini would fly into the embrace of Saturn itself, Cassini's chance for annihilation would become certain. NASA's website states the reason for this final mission. As it plunges past Saturn during the grand finale, Cassini will collect some incredibly rich and valuable information that the mission's original planners might never have imagined. The spacecraft will make detailed maps of Saturn's gravity and magnetic fields, revealing how the planet is arranged on the inside, and possibly helping to solve the irksome mystery of how fast the interior is rotating. It will vastly improve our knowledge of how much material is in the rings, bringing us closer to understanding their origins. Cassini's particle detectors will sample icy ring particles being funneled into the atmosphere by Saturn's magnetic field, and its cameras will take amazing, ultra-close images of Saturn's rings and clouds. No other mission has explored this unique region so close to the planet. What we will learn from these activities will help improve our understanding of how giant planets, and families of planets everywhere, form and evolve. At the end of its final orbit, as it would fall into Saturn's atmosphere, Cassini would complete its 20-year mission by ensuring the biologically interesting worlds Enceladus and Titan would never be contaminated by hardy microbes that may have stowed away and survived the journey intact. It's inspiring, adventurous, and romantic, and a fitting end to this thrilling story of discovery. But let's take a closer look at some of these final moments. During Cassini's grand finale, NASA became willing to trade Cassini's prospects for longevity for a chance at unprecedented levels of closeness to Saturn. This was an easy trade to make. After all, Cassini was running out of fuel, so its survival was already off the table. Making this decision meant Cassini was given the go-ahead to approach the planet closer than ever before, darting in between the rings. But what did it see? Did this unique perspective show anything we've never seen before? Let's take a look at some of the awesome sights Cassini saw during its grand finale. Well, starting with the moons of Saturn, it has seen some of the shepherd moons in unprecedented detail. This is a close approach of Atlas, a 40-kilometer wide moon near the outskirts of the A-ring. What looks remarkable about this moon is the lack of impact craters on its apparently smooth surface, making it look absolutely bizarre. Dust from the rings is collecting over the surface, particularly around the equator of the moon, smoothing it over and giving it this disc shape. A similar thing happens with the second innermost moon of Saturn, Pan. At 30 kilometers wide and found in the Encke gap, any particles from the rings that stray into the 350 kilometer wide path get swept up by Pan. This keeps the Encke gap steady and constant. Daphnis is another shepherd moon, sadly not seen in quite so much detail. But due to the gap it is located in, its effects can be seen for hundreds of kilometers. It is only 8 kilometers in diameter and is found in a very narrow gap in the A-ring called the Keeler gap. Its gravity is very weak, but it is just enough to whisk the nearby dust particles as it brushes by. This creates these waves, or a ripple effect in the nearby rings, sometimes even ripping material directly out of the ring, visible in this little trail here. Not only do these ripples move side to side, but up and down too, as can be seen by the shadows they create. I can only imagine what it would be like to sit on Daphnis and watch as waves follow its orbital path, with glorious Saturn and his many moons in the background. It would be quite the sight to behold. Talking of the rings though, Cassini has been able to capture some spectacular images. One of my favorites from the grand finale is this one, showcasing the Janus 2-1 spiral density wave. Amazingly, what you're looking at here is the result of the same process that creates spiral galaxies, just much more tightly wound. What appears to be many separate rings is actually only 2 spiral arms looping around the planet many times. So every second line you see in the image belongs to the same spiral arm. This image is part of the B ring, at a position where the ring orbits twice for every 1 orbit of Saturn's moon Janus, causing an orbital resonance. This photo gives the illusion that the image is tilted away at the top left, but this isn't the case. The illusion is created by the way density waves propagate from the planet, the wavelength decreasing with the distance from the resonance. And this is where the resonance gets even more mind-blowing. Janus, the moon that contributes to the resonance, switches positions every 4 years with its close neighbor moon, Epimetheus. Every time this switch takes place, the rings respond, creating a new crest in the waves. NASA says the distance between any pair of crests corresponds to 4 years worth of the wave propagating downstream from the resonance, which means the wave seen here encodes many decades worth of the orbital history of Janus and Epimetheus. According to this interpretation, the part of the wave at the very upper left of this image corresponds to the positions of Janus and Epimetheus around the time of the Voyager flybys in 1980 and 1981, which is the time at which Janus and Epimetheus were first proven to be 2 distinct objects. This encoding reminds me a bit of a tree trunk encoding how many years it's been alive by the amount of rings it has. Simply amazing. Apart from other beautiful and detailed images of the rings, other interesting sightings have been these little propeller features dotted around the rings in a number of locations. This image shows both sides of the rings. The top image shows the illuminated side and the bottom the unlit side. Scientists do this to compare and try to figure out details. Even though the scale of the image is only about 500 meters per pixel, the moonlet might not even be able to be resolved. You might just be able to see some trace of it in this top image, but what can be seen is that the moonlet is physically connected to the rings by this band of materials. As I mentioned, this wasn't the only moonlet trying to create a gap in the rings. Here is another, found right next to the Encke gap, and here is another, and probably the biggest out of all three. None of these moonlets are thought to be bigger than 2 kilometers, and probably have the density of a snowball. The last interesting thing Cassini was able to image within the rings is extremely small but solid objects which are formed around the F ring, potentially caused by the perturbations of some of the shepherd moons around there. They seem to be solid, as they have survived crashing into the F ring a number of times, kicking out dust and particles which sometimes then even follow their orbit, as can be seen by the haze around them. The objects themselves are not actually visible due to the dust obscuring the view. Lastly, let's look at the planet itself. As Saturn's northern hemisphere was in full summer at the time Cassini flew by, its remarkable hexagon around the pole was in full view. In the center of the hexagon is found a permanent polar vortex with the eye wall of a massive hurricane. Interestingly, the pole seems to be changing color with the season, as you can see quite clearly in comparison to 2012, where the pole appeared quite dark in color. With the assistance of other wavelengths of light, other storms are visible and can be seen dotted all over the planet, as well as bands reminiscent of Jupiter, just not quite so vivid in natural light. Also, because of the proximity of Cassini to the planet, it was able to get a good look at the planet's horizon. On the left of the image can be seen a haze in the stratosphere of the atmosphere that disappears towards the right of the image. When Cassini did enter the atmosphere on its final approach, it was thought it would not survive to even reach this haze. However, scientists weren't too worried about that. What was of particular interest to scientists is what the atmosphere consists of. Cassini would dive into that atmosphere to find that information, and would burn up in the process, making it the last readings that Cassini would ever send. But 1 week before it entered the atmosphere, Cassini was still taking images. Some of these final images are fantastic, although be aware that Cassini is not capable of real-time video capture. The videos I'm about to show you are time lapses, the splicing together of countless individual images into glorious visualizations of what it would be like to fly with Cassini on its ultimate journey into Saturn. Not all of these images are of Saturn itself. The first time-lapse we will look at is from the 8th of September 2017, only 1 week before the end of Cassini's mission. One of the main focuses of Cassini during its mission was the moon Enceladus, one of the prime candidates in the solar system to contain life in a subsurface ocean. Cassini discovered over 100 water plumes erupting through the moon's crust from this ocean, water which freezes in the space environment and has now formed the beautiful E-ring around Saturn. This ring is very tenuous, only visible when backlit by the sun, and is potentially the bluest naturally occurring object in the solar system. Here is a great view of Enceladus's effect on the densest part of the E-ring. You can see the plumes disturbing and replenishing the ring. Cassini's final look at Enceladus's plumes were captured in this remarkable time-lapse taken over a 14-hour period. On the 11th of September, Cassini was near the furthest point of its final orbit and captured this beautiful mosaic in natural light. Visible are the thickest of Saturn's rings, D, C, B, A and F, with Saturn's short shadow being cast over them. Saturn's northern hemisphere was experiencing summer during this time, which means that Saturn's most famous hexagon storm is visible in all its glory. You can also just about notice Saturn's subtle bands in natural light. What's really interesting about this image, however, is that the night side of Saturn is dimly illuminated. This is due to light reflecting off the rings, meaning Saturn's nights in the hemisphere facing the sun don't get that dark. Below the glow of the rings, Saturn is pitch black. As Cassini began to approach Saturn again on the 12th of September, it took images of Saturn's atmosphere near the planet's terminator line. Incredibly, because the Sun is so low in the sky here, huge cloud structures can be seen casting shadows that stretch for many kilometers. You may think this is a close-up of Saturn, but actually we are looking at a scene about 5,500 kilometers across. Saturn's moon Titan could easily fit in this shot. Cassini was getting closer and closer to Saturn. On the 13th of September, it peered one last time at Daphnis. And some of you keen observers will notice ripples in front of the moon as well as behind. This is due to orbital speeds of the rings and the moon. The inner ring orbits faster than Daphnis, meaning the ripples overtake the moon, exposing more ring material to the moon's gravity. On the other hand, the outer ring travels slower than Daphnis, meaning the ripples lag behind the moon. By the time the ring material reaches Daphnis on either side again, the ripples have already smoothed out. On the same day, Cassini had one last look around the Saturn system. It captured a view of Titan, a moon it focused on heavily during its mission, a remarkable world with a thick nitrogen atmosphere. It also peered at Saturn's rings, with the uneven F-ring just about visible at the bottom of the image. And as Saturn got bigger, it took one last look at Enceladus over a 40-minute period before it disappeared from view behind the limb of Saturn. The final image Cassini ever took was looking over the region where it would plunge into the atmosphere. It was nighttime here, and so Saturn is lit up by light reflected off the rings. On the final day, photos were not on the science agenda. As beautiful as they use up a lot of valuable bandwidth, and scientists wanted to get every bit of data real time before the spacecraft was destroyed. This was a unique opportunity. We had never probed Saturn before this. When Cassini first hit the tenuous parts of Saturn's atmosphere, it was traveling 123,000 kilometers per hour. The remnants of Cassini's fuel were deployed by its thrusters to keep Cassini's antenna aimed at Earth. At this point, Cassini was 1,900 kilometers above Saturn's clouds. A minute later, these thrusters were firing at maximum capacity to keep Cassini from spinning out of control. Cassini was directly sampling Saturn's atmosphere, but this atmosphere was also heating Cassini up. Just 10 seconds later, the thrusters were overcome and Cassini began to tumble, cutting off communication with Earth. Cassini's onboard computers at this point would have been trying to figure out what was going wrong. Gyroscopes and star trackers would tell the computer that it is spinning, and it would likely have gone into a safe mode to divert power in an attempt to right itself. A minute or so later, the spacecraft would have disintegrated altogether and burned up in Saturn's atmosphere. As data started arriving 1.5 hours later on Earth, this final part of the mission was deemed to be a great success. Cassini recorded data from direct analysis of Saturn's atmosphere, its ionosphere, dust particles in the atmosphere, and from magnetic field measurements, and perhaps more that has yet to be uncovered from the data. And that's the amazing thing about the Cassini mission. It just keeps on giving. Science papers and discoveries are still being made as the data it collects is analyzed and re-examined. What have we discovered from Cassini's data in the years since his groundbreaking mission? You're about to find out. But be aware, some of the things Cassini has learned about Saturn has only served to make the planet even stranger. You may think you know Saturn. Its iconic rings are the largest in the solar system, and its hazy yellow surface is both enigmatic and instantly recognizable. It is the second largest planet, the least dense, and the sixth from the Sun. And yet, Saturn is an enigma. There is a vast mystery lurking beneath its obscuring atmosphere, uncovered by the Cassini probe, one that the scientific community still does not have consensus about. Saturn behaves in ways that our conventional models claim is impossible, from its temperature, to its magnetosphere, to even the very length of its days. what is going on with Saturn, and what are our best attempts at explaining these baffling phenomena. The Cassini probe arrived at the gas giant on the 1st of July 2004. It was not the first probe to arrive at Saturn. 3 others had already done flybys. However, it was the most thorough. As we have already mentioned, it spent 13 years circling the planet, collecting reams of data using its various spectrometers, magnetometers, and other equipment. The knowledge it gave us has been a huge benefit, but sometimes only serves to deepen Saturn's mysteries. Take for example that hexagon storm on Saturn's North Pole. The edges of this 29,000 kilometer wide storm could each fit the Earth comfortably inside, and as best as we are able to tell, does not shift its longitude, remaining fixed at its location, traveling with the rotation of the planet, unlike the rest of Saturn's swirling clouds, pushed along by its up to 1,800 km/h winds. The storm is undeniably a strange one. Scientists do not yet have a full explanation for it, although there are some lab experiments that have created close approximations to hexagons on much smaller scales. But it is not alone. As the mountains of Cassini data started getting analysed in the years since the end of its mission, more mysteries have started coming in. It started with a fairly innocuous question. How long is a day on Saturn? Although we've watched Saturn in our sky for thousands of years, scientists did not yet have a definitive answer. After all, it wasn't as simple as looking up at the planet and seeing how long it took for its rocky core to rotate. Saturn's thick cloud cover obscures any landmarks that might exist on any hard surface below, and those clouds move at different speeds to the core due to the powerful wind. The rings themselves orbit Saturn at different speeds, so they don't settle this question. You can't look at how fast they orbit and hope it's the same. After all, most moons don't do this, so rings are no different. Rather cleverly, scientists do have techniques for figuring out the rotation of a gas giant by looking at its magnetic field, and it was hoped that this method might be used on Saturn. Planets with magnetic fields produce them via a dynamo effect. As the planet rotates, liquid metal in the core spins and shifts, and this colossal motion of molecules creates massive currents of energy, which in turn produce magnetic fields. One feature of this is that, thanks to this rotation, the pole of this magnetic field is always off from the axis of rotation for the planet itself. If the two lined up, the magnetic field wouldn't survive for long. So all you have to do is detect the magnetic fields around a planet, which Cassini could do, and watch as the magnetic pole shifts in a circle around the true axis of the planet. Once the magnetic pole has completed one rotation, you have your day. Only Saturn apparently does not play by the rules, and its magnetic pole is almost perfectly aligned with its axis of rotation, to an order of accuracy of less than 0.1 degree. And, in spite of dynamo theory claiming that this should be impossible, Saturn's magnetic field is alive and well. Its magnetic moment is 580 times more powerful than Earth's, and is extremely influential on the Saturn system as a whole. Scientists do not know how this magnetic field occurs, as it is impossible under dynamo theory, but no other method for producing such a field is proven. Either a planetary dynamo is at play in Saturn's core, but some other effect is occurring in the atmosphere to warp the magnetic field lines to be perfectly aligned with the axis of rotation, or we are observing a completely new method of producing a magnetic field on Saturn. So it was back to the drawing board for solving a Saturn day. Fortunately, radiation proved to be of more help. Saturn is an electrically live system. Charged ions move between the layers in its atmosphere, even between its rings and its ionosphere. Scientists noticed that Saturn emitted radio waves as a result of all the magnetic fields at play, and these radio waves rose and fell in intensity. In fact, it seemed to mirror what you might expect to see as a result of the planet rotating, higher levels of radiation would appear every 11 hours or so. As a result, scientists concluded with some certainty that this was Saturn's day length. Their initial estimate based on Voyager data was 10 hours 39 minutes and 23 seconds. It was hoped that Cassini would be able to improve the accuracy of this figure. Initially, Cassini was able to do so. But then it got really weird, because over the course of the 13 years of Cassini's study of Saturn, this number started to shift. It drifted about 1% over the course of a year, sometimes rising, sometimes falling. This almost seemed to imply that the planet itself was altering the speed of its rotation, sometimes speeding up and sometimes slowing down. To be clear, a planet as massive as Saturn should not be doing that. As such, scientists concluded that this wasn't happening, and some effect must be once again muddying the waters around Saturn. Some aspect of the atmosphere was causing shifts in the fields, making the radiation fluctuate over time, hiding the true rotation of the planet beneath a cloaking shimmer. Another key consequence of the planet's magnetic field is the auroras that shine at Saturn's poles. But while on Earth, our auroras are the result of solar wind interacting with our atmosphere, it is thought that this does not account for the auroras on Saturn. Cassini detected that at least some of them occurred regardless of what the solar wind was doing at the time, meaning that Saturn's auroras are non-solar originating. Something strange must be going on inside Saturn. It was hotter than it ought to be too. It radiates out into space about twice as much as it receives from the Sun. And while some of this may just be gravitational compression of the planet, the rest needed some other way to account for it. Ultimately, all of this needed some unifying explanation. And fascinatingly, thanks to Cassini's data, we discovered the key to all of it may lie within Saturn's gaseous atmosphere. Saturn is a gas giant. It is almost entirely made of hydrogen and helium. Not all of this is gas, as the great mass of Saturn means that the deeper into its atmosphere you go, the more intense the heat and pressure that you are subjected to. It is thought that this pressure forces gaseous hydrogen to become liquid metal. Some scientists theorize that this liquid hydrogen, or perhaps even hydrogen compressed so densely that it becomes diamond, rains down into the depths of Saturn, and the friction this generates explains some of Saturn's unusual heat. But the rest comes from the auroras. Although these are not fully understood, it is thought that they are the product of electrically charged particles coming into Saturn from its rings and moons. Whatever their source, these auroras may be creating enough heat to warm the upper atmosphere of the planet. Temperatures so hot create other effects. Where warm fronts meet cold, powerful winds are formed. It is theorized that these winds carry charged ions around Saturn's upper atmosphere, and these electrically charged winds are what is skewing the data from Saturn's radiation, causing its variance. Perhaps such motion of electrical currents might also explain why Saturn's magnetic fields are not where they are supposed to be. This could be caused by a conductive layer within Saturn's clouds, moving at a different speed to the others, creating fields of their own. At least, so goes the explanation. In all this, it should be clear that many of these answers lack final proof. Scientists are trawling through the data given by Cassini, hoping for further insights. If these are not forthcoming, then ultimately it will take another mission to Saturn to find the answers to these puzzling questions. But what about the length of Saturn's day? Thankfully, this one mystery does have an answer, and it turned out the clue lay in the rings after all. Rather than investigate the electrical and magnetic effect of Saturn on its rings, scientists realized that Saturn would also target them through its gravity. This is fairly obvious, but what was more insightful was that Saturn would not tug at them uniformly. Saturn is not a perfectly round ball. Any variance in its shape result in variance in its gravitational field. Saturn's rings were a perfect canvas to look out for such variance. As Saturn pulled at its rings with a rising and falling force, at certain locations in the rings, it would be able to detect ripples. Scientists started looking for these ripples and located them. By measuring the distance between them, it was finally possible to calculate the length of Saturn's day. They weren't far off. It was 10 hours, 33 minutes and 38 seconds. And this time, scientists are fairly certain that they've got it right. So at least this mystery was solved. And yet Saturn's other mysteries still persist. The next mission to Saturn will launch in 2027 with NASA's Dragonfly, although this will focus more on exploring Titan, Saturn's largest moon. Titan is the most Earth-like object in the solar system, as it is the only place thought to have atmosphere filled with nitrogen, similar to ours, albeit with no oxygen, and rain cycles and liquid lakes on its surface, although these are methane rather than water. So it's understandable why scientists want to give it a look. Still, it means that it may be some time before Saturn's deepest mysteries find themselves answered. Saturn breathes. The winds that might prove to be the lifeblood of the system thrum and flow across its atmosphere. Its delicate balance of magnetic fields and gravity coax at its rings, keeping them perfectly aligned. Saturn's rings are thought to be surprisingly young. Saturn may be over 4 billion years old, but there is evidence that the rings may have only formed in the last 100 million years, and they are slowly draining back down into Saturn's atmosphere. So in another 100 million years, they may be gone. This is sad to me, but I also feel strangely fortunate. If humanity hadn't arrived when we did, we might have missed this beautiful cosmic sight. It may be unscientific to say that, as the planet has no real choice in whether it gives us a gift or not, but I'm nonetheless grateful to have been witness to the enigmatic and wondrous world that is Saturn. And seeing those enigmas and wonders, all the beauty, all the scientific data, just would not have been possible if it had not been for the incredible Cassini-Huygens. This truly was one of the greatest space missions of our time. Did you think space was silent? Well, it might be for audio or compression waves, but what if you were in orbit around Saturn, listening for radio and plasma waves? The Cassini spacecraft, which orbited around Saturn for 15 years, had a radio and plasma wave science instrument on board that could pick up what you are hearing now, being emitted by Saturn and its moons. These radio waves have been compressed for our benefit, converting roughly 30 minutes worth of radio waves to a minute's worth of audio waves. This wasn't just done to create a creepy audio file, but it had real scientific purpose, which was to examine the source of these radio waves. In the case of this audio file, the source was Saturn's aurora. You see, the sun is always blasting out bits of its mass in the form of electrically charged particles, called the solar wind. Planets with a magnetic field surrounding them redirect this solar wind around the planet to its poles, where the charged particles impact the planet's atmosphere, or more specifically, its ionosphere. This impact causes particles in the atmosphere to become excited, or in other words, the collision ionizes the particles in the atmosphere, causing them to emit electromagnetic radiation. We can see this ionization with our own eyes in visible light, but aurora also emit radio waves, which we need special instruments to detect, like the one that was on Cassini. These radio waves bounce around within the planet's magnetic field, which is where Cassini picked them up. How do we know this? Through another audio file. What you are listening to here is the Cassini spacecraft passing through the bow shock of Saturn's magnetosphere. As I mentioned, Saturn has a large magnetic field surrounding it, called the planet's magnetosphere, which deflects the solar wind around it. For the first section of the audio, Cassini is outside of Saturn's magnetosphere. Outside the magnetosphere, radio sources are quiet and there is calm in the audio. Then, Cassini's orbit takes it through the magnetosphere's boundary, called the bow shock, which is the place where the magnetic field and the solar wind collide. There is a sudden increase in radio waves. Past the bow shock, Cassini begins to detect a lot more radio waves bouncing around Saturn's magnetosphere, noticeably different from the outside of the magnetosphere. But Cassini heard a lot more than just aurora. Cassini also made some close approaches to Saturn, listening closely to the planet itself. Saturn has a thick and dynamic atmosphere, with massive storms spanning the planet. One such storm sounded like this. What you are listening to here are radio waves being generated by lightning in one of Saturn's storms. It may sound small and almost puny, but remember that this is not the representation of audio you're hearing. These lightning strikes are so powerful that Cassini could detect their radio waves in space. To give you some kind of scale, scientists estimate that the lightning in Saturn's storms are roughly 1,000 times more powerful than typical lightning on Earth. To get this close to Saturn, Cassini had to pass through its rings. During flybys like this, Cassini listened. What do you think could be the cause of this audio? Cassini was travelling extremely fast around Saturn, as fast as 121,000 kilometers per hour. As it orbited through the Janus Epimetheus ring, a very faint and dusty ring, it would impact tiny particles, which would vaporize into clouds of plasma. These tiny charged explosions could then be picked up by Cassini's radio and plasma wave science instrument, and these impacts were then converted into the audio you are now hearing. The increased frequency of these impacts showed the densest part of the ring, and as the impact subsided, it indicated that Cassini was moving away from the ring again. Cassini tried this again later in the mission, except this time through a gap between Saturn and the D-ring. You'll notice this time that there wasn't a noticeable increase in collisions. At first, scientists thought that this was because the gaps between the rings were just really barren of particles. However, a second orbit through the gap revealed something different. This time, and every orbit after that, there was a noticeable increase in particle collisions. So what happened the first time? Well, as it turns out, there were particle collisions, but none of the particles in that part of the gap were big enough for the RPWS instrument to detect. Cassini had another useful instrument on board, however, called the Cosmic Dust Analyzer, which could detect particles up to only 1/1,000,000th of a millimeter in size, and this instrument did detect an increase in particle collisions during the fly-through. After passing the ring during the second fly-through, you'll also notice these rising tones. Scientists are unsure what causes these exactly, but it is reminiscent of what Cassini detected earlier in the mission. The other most interesting source of radio and plasma waves around Saturn is actually its moon Enceladus. 2 weeks before Cassini plummeted into Saturn's atmosphere, it captured this as it passed by Enceladus. These observations show that Enceladus and Saturn have a plasma circuit between the two, much like Io and Jupiter, just perhaps to a lesser extent. Although the strength of this plasma circuit surprised scientists greatly. Cassini was also equipped with a magnetometer. This is what it detected by Enceladus. During the flyby of Enceladus, it was able to detect a bending of the magnetic field, indicative of a thin atmosphere, the source of which is likely to be the jets and cryovolcanism near the south pole of the tiny moon. This geological activity draws parallels again to Jupiter's moon Io. The magnetic fields of both planets interact strongly with the ejected atmosphere of the moons, creating a flux tube, or a current of charged plasma particles. There's just one more place that I want to have a look at around the Saturn system, and that is Titan. Cassini's first major objective upon reaching the Saturn system was to launch the Huygens probe towards Saturn's biggest and perhaps most interesting moon, Titan. Although Huygens didn't have its own RPWS instrument, it did have some other instruments. See if you can guess what this is a recording of as it descended towards Titan's surface. If you guessed radar echoes, well done. Huygens used this to determine its altitude above the surface. And what about this? This is perhaps the most impressive of any of the clips I've shown so far. Why? It doesn't sound that impressive until you realize that this is actual audio taken by a microphone on the Huygens probe as it descended through Titan's atmosphere. This is it leaving the vacuum of space and diving into another world. What you are hearing is exactly what you would have heard if you had been sitting on Huygens as it descended. This gives the clip such an awe and perspective like nothing I've heard before. Somehow it's quite incredible for me to think about. We often have visuals of other planets, but I'm not really sure if there's anything quite like this out there. And there we have it, the sounds of Saturn and a couple of its moons. Today I'm super excited. Why? Because I get to show you the amazing planet that is Saturn. As far as the planets go, this is probably my favourite planet outside of Earth, and I think by the end of this video you may agree with me, because thanks to the Cassini probe, we have some astonishing imagery of this beautiful planet. I'm Alex McColgan and you're watching Astrum, and in this video I will not only give you insights into some of the spectacular Cassini images, but I will also give you an overview of almost everything you could want to know about the sixth planet from the Sun. Saturn is big. It's a gas giant with an average radius about 9 times that of Earth, making it the second biggest planet in our solar system. I say average radius because its equatorial and polar radii differ by almost 10%. It's 60,000 kilometers at the equator compared to 54,000 kilometers from pole to pole. With an average density of around 0.7 grams per centimeter cubed, it is only 1/8 the average density of Earth. However, because its volume is so large, Saturn's mass is over 95 Earths. This low density makes Saturn the lightest planet per cubic centimeter by far, and it's the only planet of the solar system that is less dense than water, about 30% less. So if you had a bath toy of Saturn that shares the same density as the planet, it would float. This is because Saturn is 96% hydrogen, which is the lightest of the elements. However, average density doesn't tell the full picture of what a planet is like. Saturn is classified as a gas giant because what we see of the planet is simply gas. It doesn't have a rocky surface under the cloud layer. However, Saturn is most certainly not gaseous all the way through. It's got too much mass for that. You see, the further into Saturn you go, the higher the pressure builds. Eventually, the pressure becomes so great that the hydrogen stops behaving like a gas and starts acting like a liquid. So, in a way, under Saturn's atmosphere is a liquid hydrogen ocean. Even further below that, it may be that there is a metallic hydrogen layer, where the pressure is so great that hydrogen starts acting like a metal. And beneath that could be a metallic and rocky core. We do know that Saturn has a very hot interior, reaching 11,700 degrees Celsius at the core. This is twice as hot as the surface of the Sun. If we look at Saturn through the infrared, we can see Saturn's glow, represented in brilliant shades of electric blue, sapphire and mint green. On the night side, where there is no sunlight, Saturn's own thermal radiation lights things up. This light is generated deep within Saturn, and it works its way upward, eventually escaping into space. In fact, this infrared image reveals that Saturn radiates 2.5 times more energy into space than it receives from the Sun. You may not have noticed, but Saturn's atmosphere has a banded pattern similar to Jupiter's. If you increase the contrast when you look at images of Saturn, this becomes more apparent. Saturn's bands are much less chaotic than Jupiter's, however, and are much wider near the equator. And ever wondered why Saturn is yellow? It's believed to be due to ammonia crystals in the upper atmosphere. But while the atmosphere of Saturn may appear calm, the planet is actually extremely active. The winds on Saturn are the second fastest among the solar system's planets after Neptune. They can be a blistering 1,800 kilometers per hour. Visible storms are also known to appear on Saturn, like this one that lasted just under a year in 2011. It had been the pattern that every 30 or so Earth years, the planet produces what is called a great white spot, which is a unique but short-lived phenomenon believed to occur once every Saturnian year. However, we have spotted a few of them over the last 30 years. If it does follow a 30-year pattern though, we can expect another one any time now. Sadly, even if it does happen, we will only be able to see it through the Hubble Space Telescope, as the Cassini mission ended a few years back. Saturn has plenty of smaller storms too, where lightning is often produced. Cassini has even detected the sound of thunder. While this might sound weak, the sound you are hearing is actually the radio waves produced by the lightning converted to audio. In reality, lightning on Saturn is about 1,000 times more powerful than what we see on Earth. Still talking about storms, but moving on to the planet's poles, we find that each pole has giant, permanent storms. NASA reported in November 2006 that Cassini had observed a hurricane-like storm locked to the South Pole that had a clearly defined eye wall. Eye wall clouds had not previously been seen on any planet other than Earth. The ring is similar to the eye wall of a hurricane, but much larger. The clear air in the center is warm, like the eye of a hurricane, but on Saturn it is locked to the pole, whereas a hurricane on Earth drifts around. The North Pole is even more unusual. There is a persistent hexagon-shaped storm that rotates with the planet, not with the atmosphere. The straight sides of the polar hexagon are each about 13,800 kilometers long, making them larger than the diameter of the Earth. Why does this happen, and to such a large scale? Well, we don't really know. However, the speed differential and the viscosity parameters between atmospheric bands here are likely to be within certain margins to allow such an unusual polygon to form. Lab tests have since been done where polygons could form in a circular tank of liquid, rotated at different speeds at its center and near the outer boundary. So this is the leading theory at the moment. Interestingly, towards the center of this hexagon, another eye wall can be found. While not anywhere near as strong as Jupiter's, Saturn does have a magnetosphere, potentially generated in the metallic hydrogen layer of the planet. It is large, extending far beyond the planet, and it is strong enough to deflect solar wind from the Sun. And much like other planets with magnetospheres, Saturn has auroras. Their location and brightness strongly depend on the solar wind pressure. The auroras become brighter and move closer to the poles when the solar wind pressure increases. The same process produces auroras on both Earth and Saturn, where electrons from the solar wind stream along the magnetic field lines directed into the upper atmosphere. There, they collide with atoms and molecules, exciting them to higher energies. The atoms and molecules release this added energy by radiating light at different colors and wavelengths. On Earth, this light is mostly from oxygen atoms and nitrogen molecules. On Saturn, it is from hydrogen. The rings for me are one of the highlights of the planet. Saturn has a prominent ring system that consists of 10 continuous main rings. While they are mainly named after letters of the alphabet, the naming conventions are a little confusing, so bear with me. The first 5 rings, from the closest to the planet outward, are the D ring, which is very faint, the C ring, B ring, which is the brightest and widest of all the rings, A ring, which is the last of the large bright rings, and then the F ring. The rings extend from 66,000 kilometers to 140,000 kilometers above Saturn's center, and are made up mostly of water ice with small amounts of dust and rocks. If we look in the ultraviolet at a section of the brightest rings, it shows there is more ice towards the outer part of the rings than in the inner part. The red in the image indicates sparser ringlets, likely made of dirty and possibly smaller particles than in the icier turquoise ringlets. If we look at a picture representing radio occultation, we can judge the size of the individual particles that make up the rings. Color is used to represent information about ring particle sizes based on the measured effects of 3 radio signals. Shades of red show regions where particles are larger than 5 centimeters in diameter, green shows particles smaller than 5 centimeters, and blues show particles less than 1 centimeter in size. Overall, it's thought that particles in the rings aren't bigger than 10 meters, and most are microscopic in size. The main rings are thought to be as little as 10 meters thick to 1 kilometer thick. We can see that the rings are not perfectly symmetrical. During the planet's equinox, the rings can get a bit wonky. Look at the top of this video where the B ring meets the A ring. Zooming in on the structure reveals ridges and spokes a couple of kilometers tall, their presence given away by their shadows. Zooming out again, we can see the scale of how many spokes there are during this period. Oscillations happen all the time in the rings though, perhaps due to the presence of a shepherd moon, or even just naturally. The differences, which can be seen all in only a day, can be up to 200 kilometers. So I've talked about the D, C, B and A rings and also mentioned the F ring. The F ring can also get quite wonky and has a perfect example of what is called a shepherd moon. It's called Prometheus, and it leaves a beautiful ripple in the F ring as it orbits. Once during its 14.7-hour orbit of Saturn, Prometheus, which is only 102 kilometers across, reaches the point in its elliptical path where it is farthest away from Saturn and closest to the F ring. At this point, Prometheus's gravity is just strong enough to draw a streamer of material out of the core region of the F ring, and that's what causes these ripples. So, what comes after the F ring? Well, this is where it gets confusing. First, you have the Janus or Epimetheus ring, the G ring, Palleni ring, and then the E ring. I find this picture amazing, as these rings are much more visible being backlit by the sun. This bright blue ring is the E ring, and you can just about see the faint Palleni ring at the top of this picture. The G ring is the next distinct ring, and again you can just about see the Janus or Epimetheus ring at the top below it. And can you see us? We are all in this picture too. Here's Earth and the Moon. The very last ring is the newly discovered Phoebe ring, a huge yet dispersed ring that extends far beyond Saturn. It's so large that if it were visible from Earth, its apparent diameter would be the size of 2 full moons across. It probably originated from Saturn's 200-kilometer wide moon Phoebe, which had been battered in its past. Phoebe orbits just outside of the ring, and probably keeps this dust contained from going outward. On the other hand, it is also suspected that dust in this ring is falling inward, eventually falling into Iapetus, Saturn's outermost regular moon. It has a bizarre combination of colors because dust from the Phoebe ring settles on it, but because Iapetus is tidally locked, only one side of the moon ever faces Saturn, with the backside of it exposed to the Phoebe ring, meaning its 2 faces look very different. So now you know about the rings. I think you'll agree that they are so interesting in their own right. Theories abound as to why they are there, but we simply don't know. We know that some of the moons are responsible for some of the material there, and we also know that some of the material there is responsible for some of the moons. And talking of moons, Saturn has at least 82 of them. They come in all shapes and sizes, and most uniquely, Saturn's largest moon, Titan, which is even bigger than Mercury, is the only moon in the solar system with a thick atmosphere around it, which I have done a separate video about here. I'm also going to throw in here that Saturn has the Death Star orbiting it, biding its time. We call it Mimas. Generally though, most of Saturn's moons are very small, only a few kilometers across. Lastly, I'm going to talk about Saturn's orbit. Saturn orbits about 9 to 10 times further away from the Sun than Earth does, and 1 year on Saturn takes 30 Earth years. Funnily enough, a day on Saturn is different depending on where you are situated. At the equator or at the poles, a day lasts about 10 hours and 14 minutes. Everywhere else on Saturn, a day lasts 10 hours and 38 minutes. The issue is, because Saturn isn't solid, it's not bound to rotate at the same speed all over. I just want to leave you with this. Few sights in the solar system are more strikingly beautiful than softly hued Saturn embraced by the shadow of its rings. The gas planet's subtle northward gradation from gold to azure is a striking visual effect that scientists don't fully understand. Current thinking says that it may be related to seasonal influences tied to the cold temperatures in the winter hemisphere, and despite all that we have learned from Cassini, Saturn remains a world of mystery. Thanks for watching. This video was in part made possible by all the Astrumnauts on Patreon. If you think these videos add some educational value to the world and want to give them more stability than the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Just sign up with the link in the description. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.